We now move from power flow to optimal power flow. Ordinary power flow asks, given injections and parameters, what is the operating state? Optimal power flow asks a more difficult question. Under physical constraints, security limits, and equipment boundaries, how should the system operate? The word optimal may refer to different objectives. It may mean minimizing generation cost, reducing network losses, increasing renewable energy consumption, improving voltage profiles, or clearing an electricity market efficiently. OPF is more difficult than power flow because it contains power flow equations, objective functions, and many inequality constraints at the same time. It is not only a calculation problem, it is a decision problem. This distinction is important. If a power flow prediction has a small voltage error, we can still check it. But if an OPF model recommends an infeasible dispatch, the result may violate line limits, generator limits, voltage limits, or security requirements. Therefore, intelligent OPF must be designed with much stronger attention to feasibility and constraint satisfaction. In this section, we will examine 3 questions. Why are traditional optimization methods rigorous but expensive? Why can data-driven methods be fast? And why must physical constraints be embedded from the beginning instead of being added as an afterthought? The shift from calculation to decision is the reason OPF is so sensitive. A state estimate can be verified after it is produced. A dispatch instruction may directly affect cost and security. Therefore, intelligent OPF must be more conservative than ordinary regression. It must know when to give an answer and when to hand the case back to a rigorous solver. This page presents the mathematical structure of optimal power flow. We can read it in 3 layers. The first layer is the objective function. Depending on the application, the objective may represent generation cost, transmission losses, renewable curtailment, voltage deviation, or market clearing welfare. The second layer is equality constraints. These are mainly AC power flow balance equations. They define the physical relationship between injection, voltage, angle, and network parameters. If these equations are not satisfied, the solution is not a valid power system operating state. The third layer is inequality constraints. These include generator output limits, voltage magnitude limits, branch thermal limits, reactive power limits, reserve limits, and other operational boundaries. Why is OPF non-convex? The main reason is that AC power flow equations contain nonlinear and trigonometric coupling between voltage magnitudes and angles. The feasible region can be complex, and local optima may exist. Traditional methods such as Newton-type algorithms, interior point methods, and convex relaxations have strong mathematical foundations. But for very large systems, mixed integer decisions, security constraints, and online dispatch, solution time can become a bottleneck. Intelligent computing is useful only if it respects all 3 layers. A fast output that violates equality or inequality constraints is not an optimal solution. It is simply an unsafe recommendation. In many simplified discussions, the AC power flow equations are replaced by DC approximations. That can be useful, especially for market studies or large-scale screening. But in this course, the full AC structure matters because voltage magnitude, reactive power, and nonlinear constraints are essential for security and feasibility. Intelligent models should be aware of which approximation level they are using. This page uses a table to show how the size of the optimization model grows. When the system expands from a 1,000 bus level to a 10,000 bus level, the number of continuous variables, integer variables, equality constraints, and inequality constraints grows rapidly. The difficulty is not only that the numbers become larger, the deeper difficulty is coupling. A generator decision affects bus voltage affects branch flow affects security constraints affect feasible dispatch and market clearing. In real dispatch and electricity markets, the model may also include reserve requirements, unit commitment decisions, inter-area transactions, renewable uncertainty, and security constraints under contingencies. Every additional business requirement increases computational complexity. Offline studies can tolerate longer computation. Real-time dispatch and market clearing cannot wait indefinitely. This is where intelligent computing may help. If a learning model can provide a high-quality initial point, narrow the search space, approximate repeated subproblems, or identify inactive constraints, it can improve practical efficiency. However, speed is not the only criterion. The output must remain feasible, economically meaningful, and explainable. For OPF, a slightly faster but infeasible result is not a success. The real goal is to obtain a high-quality feasible solution within an acceptable time window. The growth of constraints also changes the role of data. Historical OPF solutions contain information about which constraints are often binding, which variables are sensitive, and which operating patterns repeat. A learning model can use that information to guide a solver. This is different from blindly replacing optimization with prediction. This page introduces OPF computation under the Kepler paradigm. Deep neural networks can take load, generation, topology, constraint parameters, and the market conditions as inputs, and then quickly predict an OPF solution or a control policy. The page mentions Hopfield neural networks, recurrent neural networks, and convolutional neural networks. These methods approach the problem from different angles: energy function minimization, sequential modeling, or feature extraction. The biggest advantage is inference speed. Once trained, a neural network can produce an answer through a forward pass, which is much faster than solving a large nonlinear optimization problem from scratch. But OPF is not an ordinary prediction task. If the model predicts a voltage with a small numerical error, that may be acceptable in some contexts. If it predicts a dispatch that violates a line limit, a generator limit, or voltage security, the result can become dangerous. Therefore, evaluation cannot rely only on average error. We must look at constraint violation, worst-case performance, feasibility rate, optimality gap, and behavior under rare but critical scenarios. Intelligent OPF should not learn only the historical output of a solver. It should also learn why the solver respects physical and operational constraints. Without that, the model may appear accurate in normal cases, but fail exactly where the grid needs reliability most. For OPF, rare constraint violations are often more important than typical small errors. A model that is excellent on average but occasionally violates a critical line constraint may be unacceptable. Therefore, training and testing should deliberately include boundary cases. Intelligent computing should be evaluated under stress, not only under normal load conditions. This page lists the challenges of using deep neural networks for optimal power flow. The first challenge is the black box nature of the model. A dispatcher needs to understand why one generator increases output, why another generator decreases output, and why a certain line becomes binding. If the model cannot provide an explanation, it is difficult to trust it in critical operation. The second challenge is credibility. OPF is connected with grid security and economic operation, so we cannot judge a model only by average prediction error. We must check extreme cases and constraint violations. The third challenge is dependence on data. Training quality, coverage, and labels all strongly affect performance. If the training data are generated by a particular solver or a limited set of scenarios, the model may inherit bias. The fourth challenge is generalization. Power system topology, renewable output, market conditions, and load patterns change continuously. A model that memorizes historical samples may fail when the system enters a new operating regime. These issues explain why physical constraints and business rules must be embedded from the beginning. For OPF, artificial intelligence is not a shortcut around the laws of the grid. It is a tool that must work inside those laws. Explainability can also be built through hybrid design. For example, if a neural model predicts active constraints or warm start values for a conventional solver, the final decision still comes from an optimization process with known constraints. This makes the AI component easier to audit and easier to integrate into existing dispatch software. This page focuses on fusion methods for optimal power flow. A common idea is to embed physical constraints into neural networks or reinforcement learning models. There are several ways to do this. One way is to add power balance residuals, voltage limit penalties, and line flow penalties into the loss function. This is a soft constraint approach. It is flexible, but the penalty weights must be designed carefully. If the weight is too small, the model may ignore the constraint. If it is too large, the model may become difficult to train or may sacrifice economic performance. Another way is to build hard constraints into the output structure. For example, the model output can be projected onto a feasible set or designed so that certain limits are naturally satisfied. This improves reliability but can be harder to implement. Reinforcement learning introduces another issue: reward design. A reward function cannot only encourage lower cost, it must also penalize constraint violation, insufficient security margin, and infeasible control actions. Otherwise, the agent may learn a policy that looks economical but is unsafe. The central message is that intelligent OPF must keep feasibility, optimality, and interpretability together. A model that is fast but infeasible is not useful. A model that is feasible but far from optimal may not be economical. A model that cannot be explained may not be accepted by operators. Another useful idea is feasibility restoration. Instead of assuming the neural output is final, we can treat it as a proposal. A projection layer, a repair algorithm, or a short optimization step can move the proposal back into the feasible region. This is often more realistic than expecting a pure neural network to satisfy every constraint perfectly. This page summarizes the OPF section. We can organize the research content into several directions. First, we need neural network architectures that can capture the structure of optimization problems rather than only fit input-output pairs. Second, we need loss functions and training strategies that explicitly consider equality constraints, inequality constraints, feasibility, and optimality gap. Third, we need mechanisms for projection, correction, or hybrid solving so that the neural output can be made physically feasible before it is used. Fourth, we need sample strategies that cover both ordinary operating points and boundary scenarios. Fifth, we need generalization studies for different topologies, load levels, renewable penetration levels, and market rules. The conclusion is that intelligent OPF is not simply a faster OPF solver, it is a decision support framework. It may provide initial solutions, screen constraints, approximate subproblems, or support online decision-making. But every useful output must be checked against physics and operational limits. In one sentence, OPF intelligent computing must answer three questions at the same time. Is the result feasible? Is it close to optimal? And is it reliable under new scenarios? If any one of these questions is ignored, the model is not ready for engineering use. The important point is not to declare one method superior. Traditional solvers, relaxations, neural networks, and reinforcement learning each have a role. The engineering task is to combine them so that the final workflow is faster than a purely traditional workflow and safer than a purely black box workflow.